Okay, so 8.5 is all about titrations. We did a titration. I'm not being crazy here, right? We had a burette, we made it from pink, and right, we had that competition. Okay, good. I included this picture just so that you get some, like a nice picture of how we have the process go for a titration. Usually on the AP exam, it's a pretty good guarantee that you will have some sort of titration type information in a free response question. There's another one that's usually, like, definitely you're going to have this in Unit 9 that we're going to talk about in a couple weeks. But so just so that you see a picture for all the reference, I know it's not in color, sorry. But when we are trying to do acid-base neutralization reactions, we tend to do them in controlled conditions so that we can see the change over time as the reaction progresses. And so a titration does that for us to let us see that. So some vocabulary: the titrant is the solution of known concentration that is delivered in a burette. So usually in your burette, you put whatever you know is the known part, that titrant part. And then the unknown solution, called the analyte, is then put in the flask that you deliver the titrant into it. And so we can use pH meters to collect the pH throughout the entire process. And after the AP exam, we will do that. We will do a titration lab where instead of using an indicator, we'll just put a pH probe in there, and you'll take data measurements of, like, okay, I've added 10 milliliters, this is where the pH value is. And then, okay, let's add 12, like 2 more, this is what it is. And it's actually kind of repetitive because you have to make the graph and have lots of data points, but it'll be nice because we'll use the thing to graph it for us. But so we can measure that pH as we go until all of the substance that's being analyzed is just consumed. And so when you graph the information of volume of the titrant versus the pH that you collect, then we have this pH curve, or titration curve is what it could be called, where the shape of the curve really depends on a lot of things. It depends on, do you have strong acid, strong base? Do you have a weak acid with a strong base? Like the general shape will be kind of like this S, but like how steep it is versus how tall is the vertical point, all that kind of stuff, all depends on those situations. And too, I didn't include anything on this, but just a little context into this, right? So as the volume is added from left to right, the pH at the beginning is a low pH. So that means that the pH you're reading is inside of your flask at the bottom. So usually if the pH is very low at the beginning, that tells you that the acid has been placed in the flask at the beginning and you're adding the base to it. So then as more base gets added, then the pH will jump because above 7 pH is a base, okay? If it were to be the other way, which I didn't include this, but I have seen pictures of this, if it were to be that you had the base starting out and you were adding the acid to it, then it would be flip-flopped, right? So then you would start out very high with the pH, and then it would go down, dropping in pH until it reached its equivalence point, and that kind of stuff. But if you get confused, if you ever see that, it's just that they were doing it backwards than what we normally do. So the equivalence point is the point where the moles of the titrant are equal to the moles of the analyte that was originally present. And this is a very important point because this moles equals moles tells us a lot of information about like how much you actually need to add for the base or the acid, what is the titrant, all those kind of things. And so we can use this relationship in a lot of ways. Oftentimes, like I said, usually you would either do like a strong acid, strong base, or you could do like a weak acid and a strong base to do this. So if you were to do a weak acid with a strong base, the pH at the equivalence point is greater than 7. And that's because the strong base is stronger, so it makes sense that the pH should be higher than 7. If it is a strong with a strong, then the equivalence point should just be 7. Like, it's kind of like a trick question, because if it's strong with a strong, they're just going to neutralize each other at the equivalence point. And then if it was a strong acid with a weak base, then at the equivalence point, it would be less than 7 for the pH. Okay, so it's just, those are conceptual things that it's nice to recognize as we're looking at it. If a pH meter is not available, then an acid-base indicator can be used. This is what we used in our lab for the first time, right? We had that, we wanted to try and get that pink color. But it's important to note that when you have an indicator, it doesn't mark the equivalence point. It actually marks what's called the end point, which is past the equivalence point. So that's why we were trying to get such the palest of all the pinks that you could get. Because if you went fuchsia, like really dark magenta pink, you went way past the equivalence point, and so your calculations were going to be off because of that. If you're using an indicator, you want to stop your titration as close to the equivalence point as you can. So that means the lightest possible change in color that you can see. Okay, with that. And we'll talk more about some indicators next week. Okay, so did I say that already? Yeah, they're not usually the same, so you just have to be very careful. Okay. When we're reading the pH curves, that, like I started to say, the shape of the curve can tell you a lot of things. So the weaker the acid, the greater the pH value will start out. So the higher up it will start. And also, the greater the pH value will be at the equivalence point. So if you have a strong acid with a strong base, which sodium hydroxide is a strong base, then it's going to be like really, really, really low pH, and then all of a sudden it will just like drastically jump up, and then it will be a very, very, very high pH sort of thing. So you'll have a very tall length of like vertical line almost. It's not quite vertical, but almost when it's strong. And so when it's a weak acid, it moves up. We can actually predict what this is based on Ka values, because the lower the Ka value, the weaker the acid, so the higher the pH would be, okay? And so this is just talking about when we look at that actual equivalence part, that vertical section in the curve, it will get shorter and shorter as the acid gets weaker because of the fact that the acid's starting higher for its pH as it gets weaker. So when we do calculations, we're going to do example 11, which is a strong acid, strong base situation. And then we'll do a weak acid and a strong base situation. And then we'll be done. Okay? So a 50 milliliter sample of 0.1 molar hydrochloric acid is titrated with 0.1 molar sodium hydroxide. We want to calculate the pH at two situations. A, after 8 milliliters of the titrant has been added, and then B at the equivalence point. Okay? So for A, since this is a strong and a strong, we are going to do the calculations that are similar to what we did in example 8. That sort of calculation from example 8 will be what we need to do for A portion of this example. Okay? My sales stays. Good, good, good. Okay, so when we think about the reaction, right, we had the hydrochloric acid is reacting with the sodium hydroxide, and it will make sodium chloride in water. And this is all for A. I'm trying to write big so that you guys can see. And then our net ionic equation is H plus OH minus to make water, because both of the strong acid and base will completely dissociate. Okay, so The first thing that we did in example 8 is we have to figure out what are the new molarities when we first mix them together, because it's going to be a total volume change there. So for the HCl, we had originally 50 milliliters of a 0.1 molar solution. Sorry, I switched around the volume and the molarity. Sorry about that. Is equal to the molarity times our new volume, which is the 50 milliliters from the acid, plus in A, we said we added 8 milliliters. So 50 plus 8, so 58. So when they're first mixed together, before the reaction happens, when they're first diluted, the new molarity of the HCl, I got 0.086 for that one. Okay, and then same thing with the sodium hydroxide. We'll do that too, where the sodium hydroxide was 0.1 molar. And there's only 8 milliliters of that one. The new molarity times the 58 for this sodium total volume. And that time, for the new molarity of the sodium hydroxide, I got 0.0138. Or 1.4, I guess. Let's do 1.4. Molar. There. That is really, really small. Okay. So then, once we know these two values, then we have to do the before reaction after, where we use up the limiting reactant. Okay. I don't want to erase it. I don't have very much space, so I'm going to wait till everybody's done before you erase it. Or I guess I could just do it over here. That's fine. So I'm going to just put the H plus as the HCl, right? So the 0.0886 goes for the HCl, and the 0.014 goes for the hydroxide, and water doesn't matter. So this is the before the reaction takes place, right? So then next we have our reaction. So in our reaction, it's pretty obvious that the hydroxide is the limiting reactant right now. So we subtract that to use up all of the limiting reactant. So then after the reaction, we have 0 concentration of the sodium hydroxide and 0.072 molar pH plus. Okay, so then now to find the pH at this point, we just have to then take the negative log of that number of the H plus concentration. And I got 1.14 for that pH. So what this is telling us, if we were thinking about a titration curve, is that when you add 8 milliliters of the sodium hydroxide in this situation, the pH is still very low. We are nowhere near the equivalence point yet. If we were getting near the equivalence point, the pH would be like 5 or 6, closer, higher up to 7. And so that's why we know we're like not far enough along yet with our curve. Okay, so that's how you would do this for a strong acid, strong base, if you were just trying to figure out what the pH is at some point on the curve. Okay, but if we go back, now let's talk about what the pH is at the titration, at the equivalence point of the titration. This one you don't have to do any math. You could, and you would get the same answer. But the equivalence point is when they're equal molar. You have equal moles of H plus and OH minus. And so if you look back in 8.1, if they're equal molar, that means that they're both going to be 1 times 10 to the negative 7. Or what would the pH be at a neutralization for strong and strong? 7. Yeah. So you don't have to do any math for that. That's really nice, right? So for B, at the equivalence point, we know for a strong base, strong acid situation, it should just be 7, which is nice and easy. Less work is the best possible way. Okay, so that's just 2 situations that you could use with strong and strong. So now let's talk about another situation. Let's do it with a weak acid and a strong base situation. Okay, so when you have weak acids and bases involved in titration, it's also useful to consider the halfway point to the equivalence point, called the half equivalence point. At this point in the titration, there are equal concentrations of each species in the conjugate acid-base pair. So what I mean for that is with an acid, if we were dealing with a weak acid, which is what we normally do, then at the half equivalence point, the amount of acid that remains is equal to the amount of the conjugate base after it has been broken apart. And because of that, because they're equal, then that leads to tell us that the pH is then equal to the pKa. Okay? And so what that means for the pKa is just, I think I put this on a different page. At the top of page 12, I gave you the equation, the pKa equals the negative log of the Ka. Okay? So if you, how this is useful, like, less work makes the dream work. How this would be useful is if you know that you are at the equivalence point and you know what the Ka value is, all you have to do is take the negative log of that, and that would give you the pH at that point. Okay? You don't even have to do anything about the moles and the whatever. It's all just simple and straightforward there. Okay? Also, with this, since they're both like negative log of the H plus is equal to the negative log of the Ka, also at that point, that just means that the H plus value is equal to the Ka value, if that would be helpful too. Okay? So we're going to use this in example 12. I'll tell you right now, I didn't realize this. I should have given you a little bit more room with the graph. So I had to finish my calculation on the bottom. So I'm sorry that there wasn't enough space up there. But okay, so we have hydrogen cyanide gas, or hydrocyanic gas, is a very weak acid with a Ka 6.2 times 10 to the negative 10 when dissolved in water. So if a 50 milliliter sample of the 0.1 molar hydrocyanic acid is titrated with 0.1 molar sodium hydroxide, let's calculate this pH first at the halfway point of the titration, and then B at the equivalence point. So the halfway point is that half equivalence point that we're talking about here. Okay, so for the first part, this is where we're going to tie in that the pH is equal to the pKa value. So our Ka value so for A, the pH is equal to the pKa. Okay, and so to find the pKa, we just have to take the negative log of the Ka that was given in the problem, 6.2 times 10 to the negative 10. And I got 9.21. So then that 9.21 is the pH value. So that is just a relationship, just to remember. We'll talk more about that whole like pH equals pKa. There's another equation later on that we'll talk about later next week that also uses this relationship, but it's just good to know when you can recognize that you have a weak acid with a weak base, and that's what works out. For part B, we are going to now calculate the pH at the equivalence point, and this is going to take a lot more work to get to the calculations or get to the final result because of the fact that it is a weak acid with a strong base. So we are going to have to combine what we did yesterday with this, with 8.4 in order to solve for the final pH value. Okay, so the first thing we need to know, the equivalence point means that the moles are equal to each other. The moles of the acid are equal to the moles of the base, or the moles of the H plus are equal to the moles of the hydroxide. So we need to know how many moles are we dealing with for the acid. So for the acid, we know that we started with a 0.1 molar solution, and it was 50 milliliters, so that would be 0.05 liters, okay? So that means that we have, if you multiply those, I put it in scientific notation, 5 times 10 to the negative 3 moles, okay? So that is the moles of the acid. So at the equivalence point, we know that we will also have 5 times 10 to the negative third moles of base, the sodium hydroxide. So with that information, now we can solve and figure out how much of the base was actually added. So for the sodium hydroxide, we know that it was a 0.1 molar solution, and we know that we have 5 times 10 to the negative 3 moles of the solution at the equivalence point. So to solve for the volume, we end up with 0.05 liters, which is the 50 milliliters. So it just so happens that this example has the volume amounts be the same. It might not be that way all the time, or I think it mathematically has to do with the fact that the concentrations are the same. So I wanted to show that for you. Okay, so what do we do with this? Well, with this 50 milliliters, now we can do the whole process of what we did in example 9, where we have to figure out what the new concentrations are when they first mix, then use up the limiting reactant to get the excess reactant, so then we can know how to proceed to find pH. Okay, so for the acid, we're using the M1V1 equals M2V2 from yesterday. So we know that we're starting with a 0.1 molar solution, and we had 50 milliliters of that. We don't know its second molarity, but we do know that the volume is the original 50 milliliters of water plus the new 50 milliliters. So total of 100 at the end. So the molarity of the acid is 0.05 molar. To save us some time, that is going to be the same numerical number for the molarity of the base as well, because again, the amount that's being used is the same, the molarity is the same. So we also know that we have 0.05 molar for the sodium hydroxide. Okay. Now, so we have to talk about what the net ionic equation is for the reaction between these two. Well, the sodium can go away because it's a spectator ion. It has no factor into it. But the HCN has to stay together because it's a weak acid, so it's not completely dissociated. Okay, so that reaction would be the acid, the HCN, plus the hydroxide ion. And that will form, so the acid will donate a proton and will be CN minus left over, and water would be the other product. Okay, so this is now the like the before the reaction concentration, then you have your reaction, and then after. So before the reaction, we've got 0.05 for both acid and base. Water has no factor in this, but since the CN minus is the conjugate base, it is an aqueous solution. We have to consider that as a part of our reaction, and then some of it is going to be formed. So it just so happens that for our reaction, the acid and the base are going to both be used up. So we can subtract away the 0.05 for both of them. But then we'll add that 0.05 to the conjugate base. So then after we're done, we have 0 concentrations of the acid or the hydroxide, but we've got 0.05 molar of the CN minus. Okay, well, this is getting us towards our way of finding out what this is. Okay, now this is in fact the conjugate base. Okay, so it's going to be a basic solution when we're done. So we need to solve for the pH using the weak base method. All right, so I'm going to clear the screen because I don't have any more space. But the weak base method is where we take that conjugate base and react it with the water. And by doing that, then now we are going to be able to create the acid and then the hydroxide ion. So this hydroxide ion is now going to tell us the concentration of the hydroxide, which will then lead us to pH. Okay, so now we're doing the ice chart. We're not doing the reaction chart, we're doing the ice chart here. So the water doesn't matter, right? The originals are both 0 for those two, and then the CN has 0.05. So since it's a base, I'm going to use minus B and plus B for my change. So at equilibrium, the acid concentration and the hydroxide concentration will both be B, and the CN minus will be 0.05 minus B. Okay? Well, now before we set up the equilibrium expression and solve, we are given in the problem the Ka value, not the Kb value. So we have to switch it to Kb before we can use it. We can't just use the 6.2 times 10 to the negative 10 as is. We have to switch it first. So to switch that, this equation comes from your notes. I had it listed, but we didn't use it. It's at the top of page 12, that the Kw is equal to the Ka times the Kb. So to find the Kb, we just have to take the Kw, which is 1.0 times 10 to the negative 14, divided by our Ka, which is 6.2 times 10 to the negative 10. And that will tell us the Kb value, which is 1.6 times 10 to the negative 5. So then now, when we use our equilibrium, we can then take that 1.6 times 10 to the negative 5 is equal to V squared over, and remember we make our assumptions that it's going to be so small that we can just take it off. The change won't be very big, and just put in the 0.05 in the bottom. So then now, when you solve for B, B is 8.9 times 10 to the negative 4, which that B value is the hydroxide concentration. All right, so we're almost to pH. We're almost to the end. I know it's been a while. So if we just take negative log of this number, we're not going to get pH. We're going to get POH, but I like to do that. So it's easier for me if I do that. So we'll take the negative log of the 8.9 times 10 to the negative 4. And that gives us, the pH I calculated was 3.05. Okay, and then pH, because that's what the problem originally asked for, we just take 14 minus the 3.05, and that is 10.95. And just to make sure that this makes sense, that means that it's a basic solution, right? The pH is greater than 7. And that makes sense because we had a strong base to start. We had that sodium hydroxide. So at the equivalence point, we should have a pH that is basic. Last but not least, I just wanted to show this to you. Another thing that you can see from a titration curve is that you have a polyprotic acid. So the number of acidic protons in the acid helps you determine how many equivalence points it has. So in this graph right here, we would have 2 equivalence points because we have 2 acidic protons. Okay, so the number of changes you see is equal to the number of acidic protons that are there. And like the first equivalence point at the 1.0 titrant volume, that would be for the first acidic proton, and then the 2.0 would be for the second acidic proton when they're released.